Welcome everyone. It is a pleasure to present my work on approximate inference systems, end-to-end approximations for energy efficient inference at the edge. Edge inference refers to the phenomenon of performing inference using AI or DNN models on edge or end user devices. Edge devices ranging from smartphones, smart cameras, wearables to autonomous drones, cars and robots are becoming more intelligent due to the infusion of AI. This trend is only going to increase further due to the continuous growth of IoT, as we can see from this forecast. In fact, recent market analysis has shown that the total addressable market for inference is much larger than training. This in turn will promote the growth of edge AI chip industry, catering to different types of devices, as we can see from this chart. As you can clearly comprehend, edge AI is ubiquitous and edge inference is paramount. Energy efficiency in DNN inference is perhaps the most important requirement in today's edge devices. Although DNNs frequently match and sometimes even exceed human accuracy levels, this inevitably comes with challenges such as high computational complexity and consequently high energy consumption. Even after considerable research, these challenges limit the widespread deployment of state-of-the-art DNNs in resource-constrained edge devices. Therefore, there is a need for extreme energy efficiency in DNN inference. In addition to being compute and memory intensive, DNN inference algorithms are typically error resilient, that renders them with the ability to produce outputs of acceptable quality even when some of the underlying computations are done in an approximate manner. Approximate computing is an emerging technique that leverages this forgiving nature of DNNs or any other error-resilient application to increase the overall resource efficiency of the computing system. Most works have used approximate computing at lower levels of abstraction for increasing the DNN energy efficiency. Some of the popular techniques include quantization or bit precision scaling, pruning, early exit, and neural architecture search. Although these approaches most often reduce the inference latency on edge devices, they only target the energy reduction of the computation subsystem. That leaves much of the energy saving opportunities on the table. However, in typical embedded systems, computation is only one component of the entire system. In order to fully leverage DNN error resiliency and extract the maximum energy efficiency, we need to explore how to approximate the entire edge inference system, not just the compute part. Consider the example of a smart camera system, which is a popular inference-enabled edge device available today. Upon dissecting one such device, we can observe that it comprises of sensor, memory, and communication subsystems apart from the compute system. It turns out that these systems contribute a significant portion to the overall system energy as shown in this pie chart. Therefore, to maximize the energy benefits, it is important to focus not only on approximate computing, but also perform approximations across all the other subsystems. Keeping with this goal, our work shifts the focus from approximate computing to approximate inference systems and explores end-to-end approximations in such systems. In a nutshell, these are the key contributions of our work. We are the first to propose an approximate inference system or AxIS for energy efficient DNN inference at the edge. We first introduce approximations in compute, memory, sensor, and communication subsystems to exploit the inherent DNN error resiliency and investigate their impact on application quality and system energy. Using these insights, we proposed AxIS variants, Camedge and Camcloud, and synergistically employed full system approximations for maximum energy savings for a specified application quality bound. Finally, we demonstrated a fully functional prototype of AxIS that consists of a camera module, DRAM memory, processor, and communication module, all of which are approximated. In order to approximate the entire system, we first need to understand how the individual components of the overall system are approximated. The first component is the sensor subsystem, which in this case is the camera or image sensor. A very efficient way to approximate image sensor is to use pixel subsampling that skips pixels of every alternate row or column to generate an image of a smaller resolution. For example, performing 2x subsampling on a 1080p image, we skip 1 in every 3 rows and columns to get a 720p image. While for 4x subsampling, we skip every alternate row and column to generate an even smaller image. Note that the subsampling is performed in the sensor subsystem only and does not involve the processor. This drastically reduces the sensor energy at lower resolutions as observed here. The proposed inference system uses DRAM as the main memory. Note that DRAM is a volatile memory that stores data in the form of charge which leaks away over time. Hence, refresh operations are needed to restore data throughout the memory every 64 milliseconds to preserve data integrity. Following prior work, we use this refresh rate as the approximation knob. Lowering refresh rate or increasing the interval drastically reduces the overall DRAM energy consumption while introducing errors in the acquired images in a controlled manner. Note that at higher refresh intervals, the number of DRAM erroneous pages increases, further degrading the image. In the context of DNN inference, we categorize DNN-based application program and DNN feature maps as critical data and input image and pre-trained DNN weights as non-critical data and allocate them to accurate and erroneous pages respectively. Note that approximations only affect DNN weights and feature maps when the inference is executed locally on the edge processor. For approximating the DNN inference computation, we have designed a quality-driven structured pruning framework. CUSP takes in a pre-trained CNN model and structured pruning algorithm along with a set of user-specified application quality loss bound and is the first of its kind to generate multiple compressed models for the input CNN and the set of loss bounds. This kind of approximation reduces different CNN characteristics, which in turn reduces the compute energy at the cost of minimal quality loss. CUSP is a generic framework and can be applied to any COTS inference system as it doesn't need any hardware modifications. Note that structured pruning is one of the simple ways of approximating DNNs, and any other compression algorithm can be used in its place to generate a smooth QE curve. Let us take an example CNN and dive into the pruning framework for a better understanding. A CNN takes in an input image and executes the inference to output the class of the image. We use structured filter pruning and thinning to approximate the convolution layers and explain with the help of this illustration. In the convolution layer I, weight filters are convolved with the input feature maps to generate output feature maps, which are then consumed by the next convolution layer. If the convolution layer I is approximated to 50%, then 3 out of the 6 filters, as shown by the red dotted boxes, are pruned, resulting in only 3 output feature maps instead of 6, as shown by the brown dotted boxes. As the input to layer I+1 is now slimmer, its weight filters are also pruned. Finally, thinning removes the pruned connections permanently, resulting in MAC reduction and subsequently lesser compute energy as shown in the chart on the right. Pruning higher percentage of filters result in further reduction in MACs and energy. This kind of approximation affects the application quality, which is regained back to the specified quality bound by fine-tuning the CNN during the pruning phase. We use lossy compression for approximating the communication subsystem, which in this case is a Wi-Fi module used to offload the acquired image for DNN inference in the cloud server. Note that lossy compression is a very effective approximation technique as it can drastically lower the amount of data to be transmitted while incurring very small amount of error in the transmitted data. We use JPEG compression on the acquired image as the lossy compression algorithm. In case of JPEG, the compression quality represented by Q acts as the approximation knob. As we see here, setting the Q to 70 reduces the image size compared to the uncompressed image, thereby significantly reducing the communication energy while resulting in small error. Reducing Q further down to 40 compresses the image more, resulting in larger errors, but more energy reduction. These errors in the transmitted image impact the DNN inference quality on the cloud. Now that we know the individual approximations, we can apply approximations across all subsystems synergistically. We present two variants of the approximate edge inference system, Camedge and Camcloud. Camedge is a computation-intensive version where the CNN inference executes locally on the edge device. Here, approximations are performed only in the sensor, memory, and compute subsystem. On the other hand, Camcloud is a communication-intensive version where the edge device simply acquires an image and transmits it to the cloud where CNN inference executes. Here, approximations are done in sensor, memory, and communication subsystems. We devise a gradient descent based design space exploration algorithm for synergistically tuning all the subsystem approximation knobs. Now, as we see here, we have the individual approximation knobs such as the subsampling knob for the sensor, a refresh interval knob for DRAM, etc. Since this example is for Camedge, the communication knob is inactive. In the graph on the right, the y-axis shows the system energy and the x-axis shows the application quality. The user-specified quality degradation bound of 5% is shown by the red dotted line. Starting with the baseline configuration, we modulate approximation levels of each subsystem and conduct QE sensitivity analysis to measure the overall system quality and energy. After this stage, the approximation configuration with the maximum energy quality gradient is selected to update the state for the next round, as we can see from the new location of the star. In the next round, we continue the exploration from the current state and eliminate the subsystem which violates the quality bound. As we can observe, the sensor subsystem has been eliminated at this stage. The maximum EQ gradient provides the maximum bang for the buck as it selects the configuration with maximum energy savings with minimum quality degradation. This iterative pruning process is continued until no subsystem can be approximated further and the corresponding quality and energy is saved. The same process can be followed for Camcloud to find the approximation configuration with the maximum energy savings for a specified quality bound. This gave a high-level overview of our exploration algorithm, and for further details on the DAC and the inter-subsystem approximation intricacies, please refer to the paper. We prototyped a fully functional approximate edge inference system that we implemented on an FPGA-based Terasic development board. This system consists of a 5 megapixel digital image sensor, a 1 GB DDR3 DRAM, Altera NIAS2 soft processor core, and ESP room module. We also show the measurement setup we used to evaluate AxIS here. Please refer to the paper for more details on the entire setup. Note that all our results are measured and generated considering ISO work condition. This table here presents a suite of application benchmarks that we used to evaluate our proposed system. For the image classification application, we used 6 pre-trained CNNs as shown here on the ImageNet 2012 dataset and adopted top 1 CNN classification accuracy as a quality metric. For object detection, we used faster RCNN on the MS COCO dataset using mean average precision as a quality metric. Next, we present our experimental results to help understand the performance of AxIS. First, we present the system QE results for image classification application. The plots here shows the normalized system level energy savings compared to the baseline system subject to different application quality bounds. Here the y-axis shows the normalized system level energy consumption and x-axis shows the different quality bounds. As we can observe, Camedge provides 1.6x to 2.7x energy savings for quality bound 0.5 to 10%, whereas Camcloud offers 3.1x to 4.5x savings. Thereby, as we can see, our proposed approximate system achieves significant energy improvement with minimal quality degradation. To understand these energy savings even more, we depict the energy breakdown arising due to individual approximations for all 6 CNNs. In these plots for Camedge, the breakdown of overall system energy is presented with energy in the x-axis and quality loss bounds in the y-axis. The bottom bar in each of the subplot represents the baseline energy breakdown for the respective CNN. Here we illustrate the results for ResNet 101. As we can see, the contribution of sensor energy is very less. Therefore, benefits due to sensor approximation is limited. We observed 37% and 31% system energy reduction at 0.5 and 1% quality loss bound, and majority of these savings is owed to memory approximations. Whereas for higher quality bounds, compute approximations is the major component driving energy savings. We provide the same set of results for Camcloud as depicted in these plots. Unlike Camedge, sensor approximation contributes to system energy savings at a quality loss greater than 5%. We also illustrate the results using ResNet 101. Communication energy accounts for 0.64 of the overall system energy for the baseline system as shown by the bottom bar. Evidently, approximation in this subsystem yields the maximum energy benefits. At a quality loss of 0.5%, communication energy reduces to 0.05 times the system energy, resulting in 71% reduction in the overall system energy. On an average, across all 6 CNNs, the communication energy reduces by 89% at this particular quality loss. The final result shows the benefits of synergistic approximation. Here, the y-axis shows normalized system energy and x-axis shows different quality bounds. These charts clearly demonstrate that our proposed synergistic approximation methodology results in much lower energy consumption for any particular quality bound compared to applying the individual approximations in each subsystem, such as compute, memory, sensor, and communication in isolation. Hence, we conclude that synergistic approximations in AxIS achieves better energy efficiency than individual approximations. Finally, we show the results of our case study on using AxIS in the context of real object detection application. As we can see, Camedge results in 1.8x to 2.1x energy savings, while Camcloud results in 2x to 6.6x energy savings compared to the baseline system. This validates the effectiveness of AxIS in increasing energy efficiency of end-to-end object detection on edge. Finally, we summarize the major contributions of our work, which we have also stated during the beginning of the talk. In short, we systematically explored full system approximation and designed AxIS, a DNN-based approximate smart camera system, for energy efficient edge inference and demonstrated significant energy benefits compared to individual approximations. Finally, I would end my talk using this recent quote. Thank you very much.